Hello and welcome back to Introduction to General Relativity, Lecture 3. Today, in this lecture, we're going to take a deep dive into the mathematics of manifolds. So it is a core underlying assumption of special relativity and general relativity. Indeed, it's a core underlying assumption of many parts of physics that space-time is somehow a continuum, a four-dimensional continuum, and that you need at least locally. So the idea is that although within general relativity, the idea is that although space-time is not globally a flat four-dimensional continuum, at least locally it is, and it's certainly an underlying assumption of many other parts of physics that the space or the space-time in which physics takes place are continua of some sort. So at this point, I don't want to be very specific about what I mean by the word continua, but roughly speaking, we assume that it takes to characterize events, say in special relativity, we need four numbers, right? We need the time that the event took place and three spatial coordinates. Now, the fundamental difference between general and special relativity is that the geometry of this continuum in general relativity is something dynamical, so it can move or change as the space-time evolves in response to the positions and locations and distribution of stress, matter, and energy in the universe. Now, because we have the possibility within general relativity for the geometry to change, to be dynamical, we need a mathematical apparatus to describe and quantify this situation. This is crucial, otherwise we would only ever be restricted to qualitative remarks. And in course, we want to do quantitative physics, where we make predictions and precise predictions and confirm these hypotheses. Reject hypotheses, of course. We cannot confirm a hypothesis in physics. Now, there are many ways you might think of building up a mathematical theory of curved continua. And one of them, and probably the simplest, is to think of curved continua as somehow living inside a higher dimensional space as a kind of embedded surface. So imagine we have some higher dimensional space-time. I don't know, we'll call this like Rm, some ambient Euclidean space-time structure. And we want to describe, and what we need is, because we think, at least within the general relativity, we presume most of the time we live in a four-dimensional space-time. So we would need that somehow m is bigger than 4 to build up a theory of curved continua. And so you could imagine building up a theory of curved continua as embedded volume surfaces inside this ambient big higher dimensional space Rm. You could do this. And I'll just label this. So you have M is, in this way of thinking, our space-time. And M lives in this bigger ambient space, Rm. Now, you could do this. And it works, for the most part. However, it does have some operational problems or puzzles. And most, I think, pressingly is the question, do these higher dimensions exist? In the end, we sort of sidestep this problem and do things in a different way, arguably more natural way. Namely, we study curved continua in an intrinsic way, without reference to this larger embedding space-time Rm. So this Rm is like, in this approach, this Rm is what we might call the ambient space, and this is the embedding approach. So we're not going to do this. This is not the way we're going to do the things in this course, because it turns out, even though it's harder work to begin with, it turns out it is more natural and more transferable a skill. That's also something that's very important, to discuss things intrinsically. So we discuss curved continua in this course intrinsically, without reference to a ambient embedding manifold as well, or space-time. When you try and describe the mathematics of curved spaces and curved continua intrinsically, you are led to the topic of manifolds, the mathematical theory of differential geometry and manifolds. And it's this mathematical theory that we are going to occupy ourselves with for the next 10 lectures or so. It is a highly demanding part of mathematics with respect to the maths that you've already met in your physics degree. It requires a fair amount of formalism to be built up to describe describe concepts that are arguably fairly intuitive, but to do things quantitatively and precisely, you do need a fair amount of infrastructure that you have to build up, mathematical infrastructure. Really, you don't need much more prerequisites than calculus and linear algebra to discuss the theory of differential geometry and manifolds. You can get away with it, although we will occasionally in this course have to encounter the concepts coming from point set topology and general topology. I will, for the large part, mention the words that are important in the theory of manifolds coming from topology. And occasionally at the ends of videos, I might add a little bit of extra material that's optional for those of you who are interested in pursuing the mathematics of differential geometry, manifolds, a little bit more deeper and more precisely. You can take a look at this additional material that I'll add at the ends of the videos. All right, before we get started on the theory of differential geometry and manifolds, I should spend a little bit of time setting up some notation. This notation is going to be with us for the rest of the course. So it's vital that we spend a bit of time settling the notation. Otherwise, things will come out of the blue and you won't know what the symbols mean. So the first piece of notation is that of Rn, Euclidean space Rn, which I'll denote as R to the n. It's just the set of n tuples of real numbers. And I'll use this underline notation for vectors of numbers, or tuples, n tuples of numbers. We'll also need to make reference quite often, actually, to the distance, the Euclidean distance functional, which is defined on Rn as follows. Just take the difference between the coordinate, square them, sum them up, and take the square root. It's the standard Euclidean distance function. You'll definitely need to know this. You'll need to know about the Euclidean ball, BR, of radius r around a point y. It's the set of all points in Rn such that the distance between that point x and this given point y is always less than r, strictly less than r. This is also called the open ball around y. This is where we'll delicately touch upon the point set topology. Then we need to have the notion of an open set U. This is going to, for our purposes, it's sufficient to think of an open set as a set U where for all points inside the set U, there exists a positive, potentially very small number epsilon, such that the ball of radius epsilon around the point x is always within U. So an open set is, in Rn at least, is defined by this, these properties. We also want to talk about sets of functions. So we're going to introduce the set Cn, which is the set of n times differentiable functions. On Rn to R. We can extend this notion of n times differentiable to vector valued functions, although I don't think I'll be doing that for quite a while in this course. A couple of edge cases here. C0 is the referred to as the continuous functions. They don't have any continuous derivatives that exist necessarily, but they are at least continuous. And C infinity is the infinitely differentiable, infinite differentiable functions, otherwise known as smooth functions. So we'll certainly have occasion to refer to these a lot in this course. Okay, now with this notation around, we can start the long process of defining what is meant by a manifold. Now in this course, I'm going to do everything as pretty general. We're going to do things in n dimensions. So you might wonder, why are we doing things in n dimensions when we obviously live in a 4-dimensional space-time? Well, I would say there's 2, 3, 4 really good arguments why you should think about the dimension of your space-time as being allowed to change, vary, or also where you might want to be able to focus on subcases where the dimension is, say, smaller than the space-time you're in. I'd say arguably the first reason why you should do things in n dimensions in this course is that it doesn't really cost that much more effort to do it. So why not? You get a lot of generality for free. That's one good reason why you might want to consider things in arbitrary dimensions. Second thing is, we often want to restrict to a special example where the dynamics are restricted to a lower dimensional hyperplane or hypersurface in space-time. You could think of the dynamics of a particle restricted to move on the surface of a sphere, for example. That's a case where you might want to consider a space-time of an effectively lower dimension. So there it's effectively lower. A third reason is much, much deeper and comes arguably from quantum gravity. There are strong indications that the dimension of the space-time we're in, which it seemed to be 4, might be emergent from a different space-time dimension. There's hints from this so-called holographic principle in quantum gravity. Another reason why you might want to consider higher dimensions, lower dimensions, or arbitrary dimensions is that in quantum gravity we should arguably be allowed to take superpositions of space-times. And there's no principle that says that we must be taking superpositions over space-times of the same dimension. So this is a whole sort of grab bag of reasons why you might want to consider formulating your physics in arbitrary dimensions. But, you know, for the most part, it just doesn't cost much extra effort, so we'll just do that. Okay, I think we're about ready to make our first attempt at a definition of what is a manifold. Definition, right? So, an n-dimensional C infinity, so there's this notion of smoothness there already, real manifold M, what is it? It's a set. So I'm at least assuming you're familiar with the notion of set theory, basic notions from set theory, together with a collection, we'll call them O alpha, of subsets satisfying a couple of requirements. There's a zeroth requirement that I'll come back to in a minute. 1, the set O alpha covers M. So M is, there's all these subsets O alpha lying around, and M is covered by them. What does that mean? It means if you stick them all together, you get M. Another way of saying this is for every point P inside M, there exists at least one alpha such that P lies in O alpha. So although I haven't, although I'm sort of urging you not to think of manifolds as embedded in some bigger space, of course, when I draw pictures, that's exactly what I'm going to do. You just have to try and forget that there's this implied embedding space in all my pictures. So I like, this is the picture I have mentally when I'm talking about this first condition. So here, M is somehow this curvy surface, and it's covered by these sets O alpha, and every point lies in one O alpha or another. So I'm just sort of, you imagine partitioning up your space M, your set M, into little pieces, and there's at least one of these O alphas over the top of any point. Now, that's not all. So for each alpha, there is a one-to-one and onto map psi alpha that goes from this O alpha set to another set U alpha, where this U alpha is now a subset of Rn, right? Now here n makes an appearance. So notice that in the first part of this definition, the dimension doesn't even make an appearance. So M is just a set covered by some subsets. In the second part, the dimension now makes an appearance. And now the picture we have in mind is that, here's M as this curvy, presumably curvy surface. Here's these O alphas. I'll just draw one O alpha. This is M. And now we're saying there exists a map which is one-to-one and onto from each of these O alphas onto sets U alpha of our more familiar Rn Euclidean space. That's what the second part of the definition says. So what you're really meant to think of is one-to-one and onto means kind of equal. And we're really saying that each part of this curvy surface M, this manifold M, is identified with pieces of Euclidean space. So you're really meant to think of a manifold as being built up or sewn to of pieces of Rn that are sewn together, stuck together. Now the third part of the definition concerns the sewing or the gluing of these pieces. So if any of these pieces O alpha and O beta overlap, right, if they have common points, so if you take the intersection and you don't get the empty set, then you can define a new map. And this new map is composed of this psi beta and this psi alpha inverse. Psi alpha inverse exists because it's one-to-one and onto, which acts via following. So you can build this map C, psi beta composed with psi alpha inverse. And where does it go from and to? Well, it goes from the image of psi alpha intersect of psi alpha O alpha intersect O beta, and it goes to psi beta O alpha intersect O beta. I'll draw a picture in one moment to illustrate what is going on here. And these are both subsets of U beta. So I've just drawn the subset symbol vertically. This is not an intersection, this is a subset of. And before I draw the picture, so we've defined this map, psi alpha inverse composed psi beta, and if any of these two patches O alpha and O beta overlap, then this map that we've just defined is not any old map. It is a C infinity map, so it's smooth, infinitely differentiable. So in short, the definition says that map is C infinity. Now here's a picture to illustrate this situation. So here's our surface M. Here's now the case where we have two O betas, O alphas and O betas. Here O alpha, O beta, they intersect somewhere, right? This blue patch here. And now, thanks to part 2 of our definition, we know there exists a map psi alpha from O alpha to U alpha inside Rn. And under this map, we can also identify the part of the intersection there. So there it is. There is that's part from part 2 of the definition. But there's also another map, psi beta, that takes O beta to some subset of Rn. It's not important that U alpha contains the origin or doesn't contain the origin. We're not thinking the origin plays no role in the definition of manifold here. And under that map, the part of the intersection of O alpha and O beta, I colored in blue. So part 2 of the definition already allows us to draw this part of the figure. You have this curvy surface, two sets, they intersect, you have these psi alphas and psi betas, you know they exist, they're one-to-one and onto. But now you can also form a new map, and this new map is psi beta composed with psi alpha inverse. So imagine you have a point here in this set U alpha, U beta. So you have a point inside U beta, you can always, here it is, let's call it, I've drawn the point red. You can form the function psi beta inverse that just sort of goes the opposite direction to find out where that point, oops, of course I drew it wrong. We want to have this point in the intersection of these two sets. I mean, what I said was right, but whatever, we want them in the intersection. So suppose you have a point P in the intersection of O alpha and O beta. You can form the function psi beta inverse. Here it is, because psi beta is one-to-one and onto, there is an inverse. And now you look, oh, that point P, that point P lying, wait on, I'll do things a little differently. I'll call this psi beta P down here, just because later we'll want to do things that way. So the red point psi beta P has a pre-image P inside the original manifold M, but that belongs also to O alpha, so we're perfectly within our rights to form the map psi alpha, to apply the map psi alpha to that point P. And so we can draw maps going in both directions. Here I've done it in the reverse order, but we could equally well have told the story another way, right? There is, suppose P is a point in the intersection of O alpha and O beta, then you can find its image in O alpha, which we've called psi alpha P here. That little cryptic symbol is psi alpha P. That's a point inside Rn. And then you could follow these arrows a different way. You could apply to this point the map psi alpha inverse to get the point P, and then you could apply the map psi beta to find the image in Rn. If you did that, you will have just formed a map psi alpha inverse psi beta that goes between these sets U alpha and U beta. Now these maps go both ways, right? It's important to emphasize that. Now that you form that map, you can't call it a manifold unless that map is smooth. It means that all derivatives exist and are continuous. There's a zeroth condition that I've made reference to already in this video. The zeroth condition comes from general topology and is not really necessary to talk about general relativity. It's quite sufficient to use your physical intuition to say that M is sufficiently nice, and since the number of examples that we really consider in this course is not completely, is not an uncountable list of horrible beasts, but really a small list of manifolds with quite a lot of good extra structure, we don't really worry about the zeroth condition in this course, but in an addendum to this video, I will certainly, I'll spend a couple more words on the definition of the mathematical definition of a manifold, just if you're interested in those details. So the zeroth condition is that M is a topological space which is Hausdorff and paracompact. And that these maps psi alpha are homeomorphisms. I'll do it in another way. I didn't leave enough space, so I'll put some space in here. That worked, it doesn't always work. And psi alpha are homeomorphisms. Look, if you know about point set topology and general topology, then this will probably make you happy. If you don't, then don't worry about it in this course. This is not going to be crucial for your understanding of general relativity in any way, shape or form. This is really optional stuff for the mathematically minded. And as I said, the actual examples that feature prominently in general relativity have so much additional structure that we don't have to worry about this axiom. Now, these maps and sets and so on that we use to define a manifold, they have names. You've got to call them something, and we give them the following names. Are called, what do we call them? Well, if you're a mathematician, you're most likely to call these maps psi alpha charts. I tend to enjoy calling them charts as well. Or coordinate systems. That's probably the terminology that might feature more prominently in physics. And so I probably will call them interchangeably charts or coordinate systems throughout this course. Now the definition, it's sort of important to say now that the definition so far, like we're not quite done with calling this a manifold yet. The definition so far depends on our choice of O alpha and beta. O alpha, sorry, and psi alpha. Meaning, and I mean this in the following sense. So suppose let's go back to our definition, right? The definition says that M is covered by a bunch of these things called O alpha. And if we had chosen a different set of O alphas to cover M, then we would have a different manifold. So, an n-dimensional C infinity real manifold M is a set together with a collection O alpha subsets satisfying blah, blah, blah. Had we chosen a different bunch of subsets, then we would formally have a different manifold. However, it's kind of obvious that, if we choose them in the same way or as encoding the same information, we have the same manifold. So we've got to spend a little bit of time talking about this arbitrariness. So the definition so far depends on the choice of O alpha and psi alphas. And what does that mean? So to show you how absurd things are. So if we add, with the current definition, a new set, just one extra new set P, and a new chart, psi prime, let's call it, then per definition we have a new manifold, right? It's even we have a new manifold, or maybe we do, right? Maybe we add a bit more on, but we get it's a new manifold even if P and psi contain no new information. So that's a bit strange, right? You therefore have it, if you have a whole bunch of sets covering M and you add one that sort of is covered by all the original sets, and you don't actually add any information, then it's a bit strange that you have a totally new manifold, different manifold. So we don't like that. It's a bit silly. So to eliminate this, right, we don't like this arbitrariness. Probably you're already thinking of ways to eliminate this arbitrariness. Well, here's one way to do it. So we require that this covering in the definition of M and these charts, or this family of charts, is maximal. So what does that mean? It means all possible, if it is possible to add a set O alpha in and a chart psi alpha in, which is compatible with all the pre-existing ones, then you have to add it in. So all coordinate systems, see, I'm going to use this notation interchangeably, coordinate systems, charts, whatever. You'll get used to it. Compatible with 2 and 3 in our definition are required included. So if you can add a chart, you must add a chart. And then only then do you have a manifold. Okay, we've got this big long mathematical definition. Can't do physics unless we have examples. So let's get to some examples. And of course, a definition's all very well, but if you can't present a single example fulfilling the requirements of your definition, it's a pretty stupid definition. Here's a laundry list of our favorite examples in physics and pretty much in maths as well. Well, it better be, right, that our notion of a curved continua contains the original notion from which we departed from, namely space-time itself. Rn is a trivial example, right? It better be an example, otherwise we've messed up in coming up with our definition. It can be covered by one chart, of course. And what is that chart? Well, just Rn itself. And then, with psi being the identity map. Now, Rn as a manifold is required to include all possible charts, remember? So, as the thing that we call Euclidean space, it's okay to describe Rn just as this set Rn. But if you want to call Rn a manifold, well, you need to include, per definition, every cover, every chart, every coordinate system that's compatible with the pre-existing charts. And therefore it has uncountably many covers, right? Because, here's Rn, right? I'm just drawing it as a square. It's covered by the set O, let's call the set O, whatever, O1 is just Rn. But it's also covered by these three sets, suppose they go off to infinity. So O2, O3, and O4. So O2 is this yellow set here. O4 is this blue set here that goes off to infinity, saying, O3 is this green set here. It's also covered by those. And as long as we set up our, and the chart, what chart should we use for O2? Well, the identity again, right? and so on, O3, O4, and then you can add any way of covering Rn with the corresponding identity chart. That is a compatible coordinate system, compatible chart, so it must go in when you're thinking of Rn as a manifold. Rn is just Euclidean space as a set. You've constructed that presumably in some part of your undergraduate degree, but Rn is a manifold, and you didn't bother with all these charts and identities and so on. But when you want to talk about manifolds, you have to have this extra baggage of charts and coordinate systems around. So you really have to allow that to be in as part of the definition and is a required part of the definition. So when you think of Rn, you really got to think of it as, yes, your friendly Euclidean space Rn, but with all these sort of infinite ways of drawing coordinate systems on it included. Okay, what's another example? Well, space-time itself is an example of a manifold. We'll prove that, well, we'll realize it as a manifold presently. It's space-time itself, in special relativity, has a temporal axis and 3 spatial axes. And we often distinguish the temporal axis by writing space-time as like R superscript 1, 3, just to emphasize that one of them is time, one not. But as a set, and even as a manifold, but not without metric, these sets are just equivalent to R4, which is already a manifold. And all this Lorentzian stuff and so on, that comes later, right? That's, as a manifold, it is, you can identify it as a subset, the charts with subsets of R4, so it's a manifold, a 4-dimensional manifold. All this temporal stuff and Lorentz structure and blah, 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 that comes later, like you add that on. So manifolds are a pretty abstract concept. They cover a lot of different examples. Okay, the next most important example is the sphere Sn, which is, embedded in n+1 dimensions. Yeah, I know we're not going to do things with embedded manifolds, but we are, of course. Embedded manifolds are one of the best examples of manifolds, but we want to allow our structures to be intrinsically defined without reference to that embedding space. But here we go, we're going to define the sphere Sn anyway as an embedded manifold. How do you define the n sphere? Well, it's a subset of Rn+1, and the subset is defined by all those points which have unit length, whatever, unit radius, unit length inside Rn+1. Now that doesn't make it a manifold, just writing it as a subset of Rn+1, that certainly does not make it a manifold. At the moment I haven't presented to you any way of covering this set, I don't know what the coordinate systems are and so on. So we have to introduce that structure, right? Before we're allowed to call this a manifold. And so we are going to introduce, well, a bunch of charts and then leave a lot of this to the exercise for you to confirm. So let's define the following n+1, 2 n+1 sets. So what you do is you take the nth, or the alpha coordinate, you take all the points inside the sphere with the alpha coordinate bigger than 0 or less than 0, and you call those two sets O alpha plus and O alpha minus. Okay, these sets cover, so how many of these sets are there? Well, there are 2n+1 such sets, right? You've got the upper hemisphere, upper alpha hemisphere, the lower alpha hemisphere. And how many hemispheres do you have? Well, you have n+1 coordinate axes, so you have 2 times n+1 such sets, and they certainly cover Sn. Like every point features in loads of these hemispherical sets. Now, great, that's the first part of the definition of a manifold, that you need a whole bunch of sets that cover it. But that's not sufficient, right? We need more than the coordinate hemispheres to describe, to endow this set with the structure of a manifold. We need also the charts or coordinates systems themselves. And these are specified by maps from these subsets to Euclidean space. So we define the corresponding charts psi alpha plus, which goes from O alpha plus to Rn, and psi alpha minus, that goes from O alpha minus to Rn. We define them via the following definition. Just take the coordinates, the points in the set O alpha, and delete the alpha coordinate. And what you get at the end is an element of Rn. This is really crucial, right? You start with points defined with respect to this weird embedding space Rn plus 1, and then the coordinate charts delete the alpha coordinate, they're away, and then we end up with a vector of n numbers, which is naturally an element of Rn. And that's how we define the charts or coordinate systems corresponding to these O alpha sets. Now we've presented enough information to get the whole manifold. So you'll have noticed in these previous examples, we really define the manifold by specifying enough sets to cover the manifold and their corresponding charts. And then we just say, throw in all the rest that are compatible. And that's generally speaking how we'll define manifolds in general. For the rest of this course, we'll just specify enough covering sets to cover the manifold. We won't specify all the possible compatible ones. Those you just automatically add in by requiring that they are that in your example that all possible charts compatible with the ones you've already presented are already automatically included. Now there's a special case of Sn. It's called S2. This is familiar to you, I hope, right? What is it? This is the two-dimensional sphere embedded in three-dimensional space. This is what it looks like. So you've got three coordinate axes now in the case of n equals 3. And the three-dimensional sphere is, well, you know what the two-sphere is, you know what it looks like, right? So it's the sphere embedded in R3, and we can just look at some examples of these coordinate axes. So that's these hemisphere sets, hemispherical covering sets, O alpha. So let's take a look at OX plus minus. So OX plus minus is the set of all points where X coordinate, let's look at OX plus. I just want to illustrate OX plus to you. So if you remember, O alpha plus is the set of all the points in the embedding space where the alpha coordinate is greater than 0. Here the x-axis sort of points out of the screen, so to speak, and OX plus is the set of all those points on the front half, therefore, of the sphere. So it's this stuff here, but not the back half. And let's draw another one. Let's try OY minus. So here's a circle around the y equals 0 equator of the sphere, and OY minus is the set of all those points underneath this coordinate axis there. So the intersection of OX plus and OY minus is relevant in a second, is like a quarter of the surface of the sphere here. And you can go through all the possibilities here. There's 6 possible coordinate charts that we specified S2 with respect to. So now let's take a look at the transition functions, the so-called transition functions, because we don't yet have a sphere, right? We don't yet have a manifold. I've specified the sets O alpha, the charts psi alpha, but you're not allowed to call it a smooth real manifold unless these so-called transition functions are all C infinity or smooth functions. So let's take a look at this one. So, for example, you could look at the chart that goes from O alpha plus to OY minus, and it's an exercise to show that this function is given precisely by this formula. Sorry, when I said O alpha, I should have said U alpha. So this transition function goes from a subset of U alpha to a subset of U beta. If we go back to the definition here, we see that U alpha is mapped by this transition function to U beta, and it's given in R2 precisely by the formula I described, and that's an exercise, and indeed it's an exercise to find the rest of these transition functions and show they are all C infinity smooth functions. Okay, so before we go on with building up manifolds and the theory of manifolds, I just want to comment, do we need all this manifold stuff really? You know, I've sort of touched on this earlier, but I want to amplify this point. The answer is sort of no. If you want to do basic general relativity, you probably don't really need all this manifold stuff. It will be sufficient to cover many of the basic examples of the basic solutions of Einstein's field equations just with R4 as a manifold. Of course, the geometry changes, but the manifold itself is just R4 underlying it. However, really, when you want to discuss more interesting solutions to Einstein's field equations, cosmology, non-trivial cosmologies, and black holes, it becomes necessary to consider more general manifolds. You know, ones with holes in them, you know, ones which looks like donuts, and so on and so forth. And of course, in quantum gravity, you want to allow yourself to be able to sum over manifolds with non-trivial shapes. So even though the answer is kind of like for basic general relativity, the answer is no, I would argue, and will continue to argue, that yes, the answer is actually yes. And I'll write down two key examples just within general relativity where you might want to be able to flexibly consider quite different manifolds, and that's given by the examples of cosmological solutions and black holes. Now, it's all very well if you've got a couple of examples, but when you want to build up a catalog of non-trivial examples from a definition, you typically want to find a way to combine your previous examples in interesting ways. So that, you know, whatever mathematical object you're considering, or whatever physical theory you're considering, if you've got a nice definition and a couple of examples, it only starts to get rich when you can build or furnish far more examples. And for that, you want to be able to build new examples, and manifolds are no exception here. So here we want to suppose that, you know, M and M prime are manifolds, smooth real manifolds of dimension N and N prime, respectively. Then we want to use these to build new examples, and the simplest way to do this is by the so-called product construction. The product space manifold. And how do you do that? Well, you just got to take all the data that defines M and M prime separately as manifolds and somehow stick it together to get enough data to define a manifold that somehow matches your intuition of what the product should be. So we have to build up some charts, right? So suppose we have the following charts, coordinate systems, defining separately M and M prime. Then we want to be able to present enough charts for this thing that we call M cross M prime. Then, so given these two charts, we're going to define our chart for M cross M prime via psi, we'll call it psi alpha beta now. And how does it work? Well, it goes from a set called O alpha beta to a subset U alpha beta of Rn plus Rn prime times Rn prime with O alpha beta. This has got to be a subset that covers our putative new product manifold. Here it is. You just take the corresponding covering sets from the respective manifolds, and U alpha beta is of course U alpha cross U beta prime. And I haven't told you what these psi alpha betas are yet. Well, I will now. Psi alpha beta acting on a point P in M and a point P prime in M prime is defined to be, well, you know, just take the corresponding points in Rn plus N prime. And this has got to hold for all pairs P prime, which are in this Cartesian product set M prime. Okay, that then presents enough sets to cover this new product set M cross M prime, and then there's enough charts, and they're all smooth. That's all an exercise. So you've got to show that the transition functions are smooth. And then another exercise is to just, you know, we've been speaking about Rn fairly loosely the whole time as a manifold, but really I want you to realize now Rn as this Cartesian, this product space construction. Now it's kind of interesting that with just these effectively two examples of the sphere in Rn, you can realize quite a lot of interesting examples now with the product construction. So just with these two families and their products, one can build many interesting examples or relevant manifolds for general relativity. Lots of cosmological solutions can be realized as products of, say, R and a circle, so on and so forth. Or like, you know, an example that should be familiar to you is the torus, for example. You know, that's just the circle cross the circle, etc., etc. You know, then you can take the torus product with the real numbers. And now, so far I've just defined to you what is a real smooth manifold of dimension n. Now we want to build up, or want to endow the class of all manifolds with a category structure. We want to be able to talk about manifolds, different manifolds, one or two the same, one or two different. So our next goal is to endow the class of manifolds with a so-called category structure. That's just fancy talk for saying that we're going to just define what it means to have a map between manifolds. By describing morphisms. Morphisms is the fancy word for what does it mean to have maps between. Two manifolds. Okay, let's define what we now mean by a map between two manifolds. So let M and M prime be manifolds. We're going to want to define what it means to have a map from M to M prime now. And let psi alpha and psi beta prime be the coordinate charts. Here where the underlying cover is now left implied. So now we have a map of sets f between M and M prime. Remember, M and M prime are sets underlying it all. They're always sets, so we can have a map between them. We have is this really a map of manifolds? Well, it is. It's said to be a C-infinity map, a smooth map between these two manifolds if for all alpha beta the following map of Rn is smooth or C-infinity. So C-infinity is synonymous with the word smooth. Okay, so let's draw a picture representing the situation here. So here's M. Here's M prime. Here's O alpha. Here's O alpha prime. Remember, corresponding to any subset or an element of our chart, there's now our map psi alpha to a map U alpha, to a set U alpha in Rn. U alpha prime here, in Rn prime. But the dimensions are going to be assumed the same, by the way. And now we can build the map. I believe there's an inverse missing in my definition here. So F is a map between M and M prime. I believe I have a missing minus here. So we can form a map that goes between U alpha and U alpha prime by first mapping from U alpha to M via psi alpha inverse. Applying F, and then mapping down from M prime to Rn via psi beta prime. And that induces this map here. So first we go from Rn back into M via psi alpha minus, then we do the map F, which is going between M and M prime by assumption, and then we go from M prime to Rn via psi beta prime. So we get this red induced function. And this map between manifolds is said to be C infinity or smooth if this corresponding red function here is C infinity. Indeed. Good. Now, we have a notion of a map between manifolds, and now we can say what it means for two manifolds to be the same manifold. So a manifold M and M prime are the same if there's a map between them, but not just any map. We need a kind of an equals sign for manifolds. And the thing that takes the place or the role of the equals sign is a so-called diffeomorphism. So if F going between M and M prime is a C infinity 1 to 1 and onto map, and if this function has a C infinity inverse, so you can invert it and it has all the same, and it's also smooth, then we give this special function a name. We call it a diffeomorphism. Now diffeomorphism, the existence of a diffeomorphism between two manifolds is really what we mean by them being the same manifold. So if there exists a diffeomorphism, then we call the two manifolds diffeomorphic. Physics translation, they're equal. They're equal because you can show that the manifolds M and M prime have identical manifold structure. Right? They have the same, you can, when you define them via charts, they have the same, you can identify all the charts, you can identify all the transition functions, everything can be identified and set, and therefore they're equal. They're not only equal as underlying sets, they're equal, they have all this baggage on top of charts is equal as well. Now, so far, we've been talking about manifolds, and manifolds are meant to supply us with a more general notion of what it means to be a continua, or an n-dimensional continua. Now, that's all very well and good, but it turns out to do local physics, we want more structure. We want to take, we're quite greedy, we want to take as much of the structure from familiar Euclidean space and import it into our notion of a manifold. And here it's important to comment that when you come up with a definition that's meant to generalize something, it has to apply to more examples. And so if a definition applies to more examples, then you're going to lose resolution in the concepts. So if there's a concept, if there's a specific example you're trying to generalize to a more general class of things, and that example has lots of structure, then if you come up with a general definition that captures this example but a whole bunch of other examples, then you will necessarily lose some of the structure that you're trying to generalize. So you think about Euclidean space for a moment. It's familiar to you, Euclidean space, it's this flat collection of n tuples. So Euclidean space is a continua, but Euclidean space also is another thing. It's a vector space. Euclidean space is a lot of things. It's a group, a mathematical group, and all these features that Euclidean space have may or may not survive in the manifold world. When you try and generalize the notion of what a continua is, you may not be able to preserve the structure of Rn as a group. Indeed, that turns out to be the case. And you won't be able to preserve the vector space structure of Rn when you consider more general examples. A more general manifold will not be a vector space. But we want to preserve as much as we can, particularly of this vector space structure, because this helps us to do local physics. Without vectors, we aren't able to define equations of motion for test particles in our space-time. So we want to preserve as much of the notion of, say, vector as possible. So first comment is that Euclidean and Minkowski space has a natural vector space structure. i.e. V, which is Rn, is both a manifold and a vector space. It certainly can be endowed with a manifold structure, but it also happens to be a vector space. And it's a vector space globally, right? The whole space itself is the vector space. Now, the next really important comment, we've introduced the generalized notion of a continuum. We don't get to keep vector space structure when we generalize our notions. So for general manifolds, it's not always the case that the manifold is a vector space. So one loses, and even if you look at the sphere, you can see that this is the case. One loses, as an example of a manifold, one loses the vector space structure. It's too bad, hey? Because there's no additive structure anymore. Yeah, there's probably, you can think of a perverse way to add add elements of the vector space, but so maybe I should just say there's no natural additive structure that inherits or smoothly deforms the vector space structure of Rn. And so the example, one example is Sn. Or even S2, right? S2 is not a vector space, as I said. It is, however, possible to associate vector spaces to manifolds. And that's something that's rather interesting about Euclidean space. So Euclidean space is globally a vector space. You can add two elements, multiply them by scalars and so on. But Rn Euclidean space is also, if you like, an infinite number of vector spaces where associated to each point in Rn you can associate, well, Rn. Right? That sounds a bit strange, but this example of Sn I think better highlights what I mean, or S2. So in S2, the sphere, the surface of the sphere or the two-sphere, we don't have a natural vector space structure left on S2. There's no natural way to add elements of S2 and get a vector space structure. But there is actually associated to S2, or to every point in S2, a natural vector space. And that's the tangent space. So if you have a point P on S2, then we can associate to that point P the tangent space. This is the two-dimensional hyperplane that kisses the sphere at that point. So this two-dimensional hyperplane, also called tangent space at P, is a vector space, right? Even though S2 is not a vector space, we lost that structure, we still locally if you zoom in, S2 looks like R2, and therefore, and you can associate this plane to it, this tangent plane, and this tangent plane most certainly is a vector space, or a vector subspace of R3. So that works when you have this, okay, this is a bit clumsy because I told you we don't want to do things with embedded manifolds, we want to do everything intrinsically. We don't want to make reference to this embedding space. So it's a bit clumsy. It looks like it may even in fact depend on how you embed your manifold into R3. So we have a problem, right, with this idea of associating to each point in a manifold a vector space. So what if we define things, or how to define things intrinsically? We don't want to make reference to this embedding space. Can we even do this? Exclamation mark, question mark. Is it possible? Well, of course the answer is yes. I wouldn't ask the question if it wasn't possible. And it's kind of an interesting roundabout way of doing things. So what we do is we first identify this tangent space structure with some other vector space that you can define intrinsically, and then we define the tangent space to be that other space. So we first identify the vector space of tangent vectors, with another vector space, namely the vector space of directional derivatives and then we don't define tangent space intrinsically, we define directional derivatives intrinsically. Lovely little puzzle when you're trying to build more general definitions. You try and isolate aspects of your definition that capture notions, and then you search around equivalent realizations of these notions until you find something that's transferable to your more general scenario. And that's the case here. When you think of a tangent vector, probably you're thinking of it geometrically. You think of the surface embedded in Rn. You think of the tangent vector as a little arrow that's stuck with its base on the surface, that's tangent to the surface. And then the tangent space of such vectors is kind of easy to realize in your mind. But that picture you can't draw when you're not allowed to make reference to this embedding space. So we now limit our thinking, and we say, okay, we're not allowed to make reference to the embedding space anymore. Could we come up with an equivalent notion of a tangent vector? And the idea is, right, to every tangent vector, there's a one-to-one and onto map between tangent vectors and directional derivatives. And amazingly, directional derivative is a notion that you can define intrinsically. So that's where we're going to end the video for today's lecture. In today's lecture, we introduced the notion of a smooth manifold as a way of generalizing the idea of a continua, or a four-dimensional continua, to from Euclidean space to a more general setting. We also commenced the discussion of tangent space of a smooth manifold. Thank you very much, and I look forward to seeing you in the next video. For those of you who are sticking around, I'm just going to spend a couple of minutes diving a little deeper into the definition of a smooth manifold. This material is not required for the course. However, you might be curious how to define a smooth manifold in a mathematically rigorous way with reference to some aspects from point set and general topology. So that's the purpose of this additional hazardous terrain track of this video. So now I'm going to present to you the formal mathematical definition of a smooth manifold in its full completeness. So really, to do things properly, you have to first introduce the notion of something called a locally Euclidean space M. So if you want to define a smooth manifold or a more general class of manifolds, we want to at least come up with a notion of something that you might call a locally Euclidean space. Now, a locally Euclidean space M of dimension D, what is it? Well, it's a Hausdorff topological space so you have to remember what that is. To every point you can put an open set around to any pair of points that separates them. Hausdorff topological space M for which each point has a neighborhood homeomorphic continuous function, continuous inverse, to an open subset of Rd. Okay. So in building up the fully rigorous mathematical definition of a smooth manifold or a manifold of class CK, we need to have this underlying structure of a locally Euclidean space first. So following this route, we are now able to commence the full definition of a differentiable smooth manifold by layering on additional structure on this definition. So the next layer of structure that we add on is the notion of a differentiable structure, calligraphic F. So a differentiable structure F of class CK, where 1 is less than k is less than infinity, less than equal to infinity, on a locally Euclidean space M. What is it? Well, this is the part of the definition which captures sort of parts 1 and 2 of the definition I presented in the main lecture. A locally Euclidean space M is a collection of coordinate systems or charts O alpha psi alpha, such that alpha is in some indexing set A, such that, well, A, these sets cover, when you union over all these OA or alphas, they cover M. B, these transition functions are CK, or at least CK for all alpha, beta in these indexing sets, and C, the collection F is maximal. With respect to B. And this is the structure that captures parts 1 and 2 of our definition presented in the main lecture. And finally, now we come to a d-dimensional differentiable manifold. Of class CK. And this notion can actually be beautifully generalized to quite a big, a much larger class of structures. So CK can be generalized to C infinity. Well, that's essentially included in the definition already, but complex structures etc. There's lots of ways to generalize this notion of a differentiable structure, and therefore you get different things, such as complex manifolds. Is a pair, what is it? It's a pair of a locally Euclidean space and a differentiable structure d-dimensional second countable locally Euclidean space M together with a differentiable structure. Of class CK. Okay, so that's the end of this additional hazardous terrain track of this video. As I said at the commencement of this additional section, this material is not required for this course. It is only presented for those of you who are curious to see where these definitions lie in the context of rigorous mathematical definitions. That's it for now. Thank you and goodbye.